Oh, that's great. Thanks, Harry. Okay, like I said, today we're going to talk about scheduling. We're going to talk about a very introductory set of algorithms for scheduling that might be used in an operating system scheduler and would be used to divide up the processing elements amongst the different concurrent entities that we've got running on our system. So threads, processes, whatever you want to call them. Okay. So what is the purpose of a scheduler? What's the purpose of scheduling as a whole? There are a couple of different reasons that we might want to use scheduling. The first would be simply we have some resources that we have a limited number of resources, and we need to divide that access between different entities that are trying to use them. And we might just be doing that as entities request access to those resources online at arbitrary times. We need to assign the resource at every instant to some entity that requests it. And the second one would be where we're actually trying to predict ahead of time what the load might be on a particular resource. So, for example, we want to offline, given a known set of requests for different resources at different times, we may want to simulate that and predict the best possible order in which to give access to those resources to that set of entities. And so then we can use those predictions. If we're using those predictions, say at compile time of a program, we could actually determine whether it's feasible to execute a set of concurrent programs on a system given our constraints, or if it's not feasible, what level of resources would be required to actually make it feasible. Likewise, if we want to do the predictions at runtime, we can be constantly predicting and re-predicting on the fly at runtime. That might allow us to determine, for example, whether to allow new requests for resources or whether to move certain entities to other areas of the system. So, for example, you're Amazon, you operate a whole lot of servers. Knowing whether you can schedule additional virtual machines onto a particular piece of hardware and still satisfy the availability and the performance promises that you've made to your customers, or whether you're going to need to provide additional hardware to meet your service level agreement. That kind of use of prediction is quite important to those kinds of operators. Okay, so we're either simply just allocating resources as we get requests, or we might be predicting. Okay, so when we're thinking about scheduling, what kinds of criteria might we be trying to optimize for? This is really important to think about, because as you'll see, it turns out that depending on which criterion you're trying to maximize or minimize, the optimal scheduling algorithm will change. There is no one best scheduling algorithm for all possible criteria. It's provable that such an algorithm does not exist. Okay, so we may be looking at two different dimensions. So one dimension we might just be interested in is sort of raw performance. We want to get the fastest or the absolute lowest response times or turnaround times. And the other one might be predictability. We don't care so much about whether our system is blindingly fast, but we want to ensure that our system does the things that we need it to do in a predictable time frame. There's no statistical possibility that we get some exceedingly long response times. Okay, so along those two dimensions, we can focus, but we can also look at different metrics for scheduling systems. So we could look at metrics from the point of view of the process or the individual user. Imagine you have a system that's shared amongst many users or many processes. So from the point of view of an individual process, we might be interested in wait time. So how long is it until this process gains access to the CPU? So how long until it's first scheduled? And response time might be quite similar in how long until the process gains access to the CPU and has had enough time to compute and deliver some response to the user. Or we might be interested in turnaround. So from when the process is first requesting access to the resource, so the CPU, how long until it's completed its use of that resource? So how long until it's done all the computation that it needs to do and return the result? And we'll see that scheduling for these two different criteria might lead to very different algorithms. From the system's perspective, the system itself may not care about any one individual process or user. It might be trying to maximize things across all the users or all the processes in the system. And so we might be looking at metrics like throughput. So in a given time frame, what is the maximum amount of work that we can get done? Probably not so much interested in minimum amounts of work in a time frame. Well, I suppose we might be interested in maximizing the minimum amount of work that could be done in any time frame. And therefore reducing the idleness of the system. So utilization is potentially a related thing. So if we have a set of resources like CPUs, we might be interested in trying to maximize the utilization. So making sure that each one of those CPUs is busy for as much of the time as we can. So if you're operating, say, a large high-performance computing system like Gaudi at the ANU, you have many nodes that are available to users. It's a very expensive system. It's pretty bad if half of that system were to be sitting idle, waiting for a job to come and fill it. You're wasting money there. So you might be interested in finding jobs to pack in and run on any idle CPUs that are currently available so that you can keep those CPUs utilized all the time. Okay, yep, so there's some people definitely interested in doing the minimum amount of work. That would actually be, that's I think one definition of intelligence, Harry, is working out how to do the minimum amount of work in any situation. There is a philosopher who has exactly that as a definition of intelligence. I'll look it up for you. Yeah, so that, I mean, there may be different scenarios in which you might want to minimize or maximize any one of these metrics. And Xiangyu, yeah, so for some systems, we may not care so much about overall throughput or utilization. We may be much more interested in making the system as predictable as possible. You can imagine particularly real-time systems where it matters intensely whether a particular result happens in a given time frame. Say you slam your foot on the brake in your car, or you pull back on the joystick in an airplane, trying to raise the flaps or whatever it is. You can imagine that a particularly long response time in those situations, if the computer takes a very long time to process the brake request, and you're just sitting there, it's just sitting there doing other things, maybe handling your stereo while you're hurtling towards the car in front, that would be really bad. So you in that case, for those real-time systems, you need a very predictable response time. There may be a maximum response time for something that you're willing to allow. Okay, so first of all, we need to think for our system which of these criteria we're interested in maximizing, and there's always going to be a trade-off. We may be interested in multiple of these criteria, and we may need to choose a trade-off between two or more of them. Okay, the other thing that we should be aware of is the different timescales on which we might be performing scheduling. So in a typical system, there may be multiple timescales on which particular operations can happen. So thinking back to our operating system scheduler from much earlier, I think week 1, we were talking about operating system scheduling, and thinking about the cycle that we have between processes that are ready to execute, processes that are actually executing on the CPU, and they may be going backwards and forwards between these two states, ready and executing, depending on time slicing or preemption. And then we also have the possibility for processes to be blocked waiting on some external stimulus. For example, a process performs some long-running I/O operation, and so it's blocked until that operation completes. All right, so you could think of this as a short-term scheduling cycle. The switching between ready and executing is going to be a very fast operation. It's going to be done on the order of milliseconds, and the blocking and unblocking is potentially instantaneous, or almost instantaneous in the order of a few machine instructions. We can add to that a slightly longer term, a medium term cycle. When we're thinking about suspension, we're thinking about swapping processes in and out of memory. So as you can imagine, this is a very expensive operation to do, to write a large part of the memory out onto a secondary storage. It's going to be very expensive, and so if we're going to add this kind of operation into our scheduling algorithm, we're going to be thinking on much larger timescales. And so this is potentially we're going to need to think about multiple levels of scheduling algorithm that handle these short-term and medium-term timescales. And we could even add even longer timescales like batch jobs, where we have users submitting jobs to a batch. They're creating jobs and putting them into a queue. And at regular intervals, perhaps through some kind of regular job like a cron job, jobs are taken off this batch queue and added to a ready queue, and now they're ready to execute. And so this batch queue may be held in an external system, and the cron job may only run infrequently. And so you may get large numbers of jobs appearing every few seconds or even minutes in the system. And so yeah, you may have multiple levels of scheduling to consider. Okay, so we're going to mostly focus today on a single level of scheduling, a short-term scheduling cycle, and we're going to mostly look at some relatively simple algorithms that you would expect to run on single CPU systems. So we're just focusing on scheduling a single resource, in this case, a CPU that's performing time slicing and multi-programming between multiple different entities. Okay, so to set up this simple scenario, let's imagine that we have one CPU and three types of processes, or rather, we have three processes. You could think of it as we have three processes that frequently request access to that resource. So the green process at the top requests access to our CPU on average every 16 units of time, and it's a long-running process. So every 16 units of time, it requires the CPU for 8 units of time. So it's going to execute for a full 8 seconds until it's completed, and then at a point in the future, again 16 units of time later, another one of these green processes will start up and require the CPU for 8 units of time. Maybe we can call these units of time seconds. It just makes it easier. Okay, and then we have a medium length process. The blue processes, on average, every 12 seconds, they're requesting access to the CPU, and they only need it for 3 seconds, so they're much faster to execute. And this one is more sporadic. It's not exactly regular. As you can see in this example, it sort of requests the CPU for 3 seconds, and then 5 seconds later it requests it again, but then there's a long gap up to 24 seconds, and then it does it again twice. So the processes don't have to be exactly regular. It makes it more fun if this one's not 100% regular. And finally, we have a very short running process. Every 4 seconds it needs the CPU for 1 second, and that's exactly regular again. Okay, now it should be apparent that if we sort of look at the average time TI between instantiations for each of these processes, and we also look at the constant computation time, so if we round all of these up to say 16 seconds, maybe that works. It should be obvious that this process needs the CPU for half of the time. This process needs the CPU for a quarter of the time, and this process needs the CPU for a quarter of the time. So together, the CPU should be able to handle this load, right? There is enough resource available on average for the CPU to handle all of this. So the question then becomes, how does the scheduler give access to the CPU? What's the correct order in which to execute processes? Which process should we execute next at any point in time? Okay, so Matthew, we'll go at the end, we'll talk about multiple CPUs, I think. So it's probably better to start with single CPUs, and then we'll go on to multiple CPUs if we get some time. Ask me again at the end. Okay, so Xiangyu's already said, well, first come, first served. Yep, so that does seem to be, like, that's probably the most obvious and in some sense the most sensible approach to do here. So first come, first served is a really simple rule. At any point in time, which process should you execute next? Well, just execute the one that arrived first in the queue. So this is, this is what a lot of shops do when customers come through the door. That, there's a single queue, and customers are just served in the order in which they arrived. That seems pretty fair and reasonable to a lot of people. Okay, so what properties does this have? Well, so we have some fairly variable waiting times in the sense of the waiting time being the length of time between when the process is requested. So down the bottom, you can look at the left hand of any of these bars. That's when the process requested access to the CPU, and the difference between that and when it actually got access to the CPU. So in this case, this blue process here requested access at time 0 and got access at time 8. So that's the difference. This pale blue bar is the wait time in that case. And for some of these processes, you can see the wait time is quite long, up to 11 seconds. The average isn't too bad. And in fact, one of the most interesting things here is that if you have multiple processes arriving simultaneously, so you actually can't distinguish, or maybe you're getting them non-deterministically arriving just instants before the other. The order in which they arrive is going to make a big difference to the outcome of this. So in this case, we've shown these two processes, green and blue, as arriving at the same time. But you can imagine one of them must have been first in a concurrent system. And so if you just switch it around, you get a very different result in terms of scheduling. So we get a different average, we get a different average turnaround time as well. How long is it between when the process was requested and when it was complete? So when it's finished use of the CPU. One nice property of first come, first served, other than it's really simple, which is a great property, obviously. Another nice property is that you do actually get the shortest maximal turnaround time. The turnaround time here is 12, and I don't think you can actually do a lot better than that, just because of the particular ordering in which these processes come in. It really doesn't matter which way you reorder things. You can't find a way of reordering the execution of these processes so that it doesn't actually make the turnaround of another process worse, even if it makes the one that's currently the longest better. Okay, is it possible for the green process to go first? Yes, it is. Sorry, that's what I showed on the previous slide. So, right. So, yes, you can view, because these processes both arrived at the same time in a concurrent system. One of them must be treated as coming first. Simultaneous means that one of them came first, but we don't know which. And so, depending on which one we choose as first, we either get this outcome or we get the outcome where we run the blue process first. And like I said, it can make a big difference to the behavior of the system in terms of average, both waiting time and turnaround time. Yes, turnaround time is from when you requested to when the process is complete. Exactly. Why would you be interested in waiting time? Well, you may be interested in wait time because, for example, the process is supporting some kind of interaction with a human or with the outside world. And obviously you can't interact with the outside world unless you're actually being scheduled to run. So think about, say, a process that's supporting a GUI on your phone or something like that. In that case, the waiting time will be important because you need to ensure that for just responsiveness of the system, that you're scheduled in a reasonable amount of time. So if your waiting time is really long, the user will experience that as the system effectively hanging. They press a button and nothing happens. So for a system where you're interested in interactivity, your waiting time is going to be important. Okay, so we could do better. Another kind of obvious fair approach might be just to divide the resource equally amongst all the processes that are currently requesting access. So we call this round robin because we just go around in a circle through all the processes that are currently scheduled, and once we've reached, and we give them all a certain slice of time, and then once we've reached the end of that, we go back to the first process and give it another slice of time, just going around. Okay, so this seems nice and fair. Every process gets an equal slice of time, one after the other. And this seems like it has the nice property that we can improve the response time. We can reduce the wait time significantly. And so compared to the previous example, we had a wait time potentially as long as 11 before a process was scheduled. We've reduced the wait time a lot here, down to 5. Right, okay, so sorry, Harry, I obviously didn't explain this too well. The length of these bars is CPU time. So for these processes, we're ignoring things like I/O or other resources. We're just thinking about processes that just need CPU. They're free to execute all the way through to completion. There's nothing that can block them other than that they get preempted by some other process. So the scheduler decides not to run them. So they just use CPU. Okay, so the length of the bars down the bottom is how much time do they need? So when are they requesting access, and how much time do they need? And the length of the bars up the top is which process is actually scheduled at any instant of time on the CPU. Okay, hope that makes sense. Okay, so round robin seems nice and fair. It's allocating equal shares, and it reduces our initial response time a lot. But unfortunately, the result of doing that is that we can potentially extend the turnaround time, the time to completion, significantly for longer tasks. And so you can see in this example, the green task is having its turnaround time extended significantly because it needs the CPU for more time. That gives the CPU that gives the scheduler more opportunities to interrupt it and replace it with other tasks. Okay, so I guess another point that I should note here is that with first come first served, the way it's shown here, there's no preemption. Each of these tasks, once it starts running, it's going to run to completion. With round robin, obviously this requires preemption, so it's requiring the scheduler to interrupt the process and give the CPU over to another process at regular time intervals. Okay, so it's great that we have a bounded maximal waiting time that's going to allow us to be responsive, but it does come at this cost that if we have very long tasks, we're going to get apparently very poor performance on those long tasks. So this will tend to favor the short tasks over the long tasks. Okay, so which one of these is universally adopted? I don't think either of these are commonly used in operating systems, but they might be used for other purposes. Okay, we've got some more to look at. So let's keep going. What next? So if we're allowing preemption, we could start to notice some things. So if we were to notice that the long tasks under round robin are being extended, we could think, well, maybe we can improve our maximum turnaround time. We can reduce the maximum turnaround time by say, trying to execute the jobs that have the most that have the longest to go until completion. Or we could try to do other things, like we could try and reduce the minimal or the average turnaround time by trying to complete tasks that don't have very long to go. So let's see if we can use the task runtime to make better choices. Okay, so another alternative might be shortest job first. So in this case, we look at the total runtime of the process, and of all the processes that are currently queued up waiting to use the system, we pick the shortest one and execute that to completion. And then we go back and do it again. If in the meantime more processes have arrived asking for this access to the CPU, well, we just add them in priority order from shortest to longest. Yeah, okay, so this actually allows us to minimize the average turnaround time. So this avoids the scenario that we had back in first come, first served, where we had some tasks that were quite short, but were waiting for very long periods of time to get access. So this, for example, this blue task here was waiting for a very long time to get access to the CPU because it was being blocked by other tasks. So if we're applying shortest job first, we will tend to reduce the turnaround time for the shortest tasks, of which in this case we have more, and that will tend to reduce the average turnaround time. It doesn't help us much with the maximum turnaround time. In fact, I think it probably makes it a little bit worse, but on average, things will get better. So again, we're preferring short tasks, as we did with round robin. This is great if we want to avoid task switches. So Theodore asks, is there a cost, when we're looking at round robin, is there a cost to doing these constant task switches? And the answer is, yep, absolutely. Task switching is expensive. It's not just the cost of executing the scheduler code and doing that context switch of the process control block and so on. There's additional costs in most systems. There's going to be additional costs due to for example, cache and page tables. So if we have large amounts of the memory required by each of these processes has to be stored in cache, there's a limited amount of cache resource. And every time we switch between processes, we're using different areas of the memory, and so we need to pull those areas back into higher levels of cache, and that will be expensive. So by switching constantly between processes, yes, Theodore, that's going to overall, that's going to increase our turnaround time, our average turnaround time. So we don't want to switch too rapidly. If we make these time slices bigger, we do fewer switches. We spend less of the CPU time on those switches. But I guess then the downside is that we don't get such an improvement as we previously saw in responsiveness. So now there's going to be a longer minimum response time. Okay, so again, we have that trade-off. We really, there's no correct answer, there's no optimal answer there for all systems. It's going to depend on properties of our hardware. It's going to depend on what we're actually optimizing for, which criteria is more important to us. Okay, Xiangyu says, in the shortest job first, does there exist starvation? Yeah, I think, wait, no, here we are. Okay, I think you're probably right, Xiangyu, in that if you were to actually have enough shorter jobs arriving to prevent the longer jobs ever getting access to the CPU, then yes, I think you could have a situation where a long job is starved indefinitely, or at least, let's see. Let's think about a more formal way to say this. So in this particular scenario, there is enough CPU available, and say these are all of the jobs that are ever executed on our system, and at time 48, our system shuts down. There is enough CPU time to execute all of these jobs. So in this case, it wouldn't be possible for a job to be starved forever. Even if we move all of the green jobs right to the end, they will eventually get executed. assuming that no more of the red and blue jobs arrive. But I think in general, Xiangyu, you're right that you have a system that doesn't end. So most systems we hope that they remain up. My servers at ANU just stay up until we need to install a critical kernel upgrade, something like that. In a system like that, yes, it would be possible that a long-running job that should otherwise be scheduled in a reasonable amount of time actually ends up getting starved by these shorter running jobs indefinitely, because they just keep appearing and bumping it further down the priority queue for execution. Yeah, so there's no maximal bound on turnaround in this kind of scenario, which is pretty bad. Hopefully your system is not fully utilized, and so everything eventually gets executed. Okay. So, and again, the arrival sequence of tasks. So if we just, again, we've got these two tasks, green and blue, that arrive simultaneously at the beginning. If we were to say that blue arrived first, we end up with a very different schedule. So it's very sensitive to the arrival sequence of the tasks. And we get different results for those average values in both cases. Okay, so shortest job first seemed to give us a nice property of average turnaround time, first come, first served gave us a nice property on our maximal turnaround time. It gave us a short maximal turnaround time. And so we might want to try and combine these two. We maybe want to find a nice intermediate point between these two. So we might look at, for example, highest response ratio first. So this is a scheduling algorithm in which we look at the amount of time that a process has been waiting to access, and the amount of time that we know that it will require to complete computation. And we use the ratio, the sum of those two things, to the process's total computation time, and we choose the process that has the highest ratio there. I think that's right. Yeah. So what this is going to do is tend to increase the preference to execute a particular task by the amount of time it's been waiting. So the longer a task has been waiting, the more likely it is to get access to the CPU next. So initially, when the green task comes in, it's not preferred because it has such a long computation time. But over time, as it's waiting for the CPU, this wait time WI increases, and so the ratio increases, and so we tend to prefer that task. Okay, and so this will hopefully avoid the starvation problem, because eventually a task that's been waiting a really long time must be preferred over a brand new short task. Okay. This is going to give us a few more switches. It's going to give us a worse average turnaround time than shortest job first, but it will give us a better upper bound on our turnaround time, a better maximum turnaround time than shortest job first. Okay, so this seems to be a nice compromise between the two. Okay, Xiangyu's asked the question that I was hoping somebody would ask, which is, but how do we predict the computation time of the process? Yes, this is a really important point. So if we just quickly go back through these methods. So looking at the first couple of methods, first come, first served, and round robin, neither of these rely on the computation time. In both cases, all they're doing is looking at a set of processes that are currently asking for access to the CPU, and they're choosing one process to execute. They don't know how long these processes will actually take. They don't need to know that. Oh, sorry, Wenxi, I missed that comment. Okay, anyway, thanks Wenxi, and thanks Harry for pointing that out. Right, so these are very simple algorithms, and they don't require a prediction of the computation time. But when we come to shortest job first, like it sounds, we pick the job that has the shortest computation time, And same thing for highest response ratio first. We need to know the computation time of the job. Okay, so in general, this is not going to be possible. For most processes on your operating system, you don't know how long they're going to execute for. In fact, there are fundamental results in computer science that tell us that we can't, in general, predict how long a process will take to execute. In fact, the program that will tell you how long a particular program will take to execute must or can in theory take as long as the program itself to run. So that's not much use to us. We wouldn't want to have an operating system scheduler that relied on us first running each process to completion before then deciding whether to schedule it for execution or not. We'd need to double the size of our hardware at least. This would not be a viable method of scheduling. So unfortunately, if we can't predict the computation time for a process, then shortest job first and highest response ratio first really aren't going to work for us. And another alternative, which we will look at, that again requires knowing the computation time of the process, shortest remaining time first. This also requires preemption. So we might decide to time slice again between processes, and at each time slice, we look at all the processes that are still waiting to execute, look at the remaining computation time for each of them, and pick the one with the least remaining computation time. So again, we're trying to optimize the average turnaround time. Again, we're going to prefer short tasks, and this has the same problem that we saw with shortest job first, that we could starve long tasks, just like Xiangyu was saying for shortest job first. Okay, but again, we need to know the computation time of the processes or the tasks. If we don't know that, then we can't decide which one is the shortest remaining time. Okay, so none of these three, shortest job first, highest response ratio, or shortest remaining time, none of these are really feasible for a general operating system scheduler. Why even mention them? Well, there may be cases where, particularly in prediction, where we're trying to optimize a schedule of tasks ahead of time offline, where we can actually predict computation times, in which case we might apply that. But for a general operating system, you won't find any of those three implemented. And hi Nicholas, good to see you online. Absolutely, scheduling is not a solved problem. It's quite amazing that even though we've had multi-programming and we've had time slicing in computing for at least 60 years, and people have been working on scheduling that long, it's quite amazing that it's really still an active area of research, and that even heavily used operating systems like Linux and Mac OS still make fairly major changes to their scheduling algorithm from one release to the next. Okay, so just a nicer algorithm. This is an algorithm that is actually about 60 years old. It was developed in the early 60s for time-sharing computers. Kobato, I think, was the one of the initiators of this, and this is actually used as the basis for some operating system schedulers, including, I think, Windows Scheduler. The multi-level feedback queue. Okay, so the idea here is, instead of having a single queue of processes waiting to access the system, all of the previous methods that we looked at, you could really just think about all the processes waiting for access as being in one queue. Whether we order those processes according to when they arrive, first come, first served, or according to how long they'll take to execute, like shortest job first, we just had a single queue. So now we're moving to a situation where we're allowing multiple queues for different processes. And the idea here is we give each one of these queues a priority, and we can have as many orders of priority as we like, really. And when new tasks arrive, they're first admitted to the priority 0 queue, so the top priority queue. and they'll move up or down priority queues depending on certain events in the system. So what the CPU is always going to do is dispatch processes from the highest ready queue. So it's going to look, first starting with priority 0 and then move down, looking for processes that are ready to execute. And it's going to dispatch them for different amounts of time. So they're going to get different lengths of time slice depending on which queue they came from. Priority 0 gets 2 to the power of 0 time slices, 1 time slice in other words. Priority 1 gets 2 to the power of 1, so it'll get twice the amount of time on the CPU, and so on. Each level down in the priority queue is going to get twice the amount of time when it executes on the CPU. Okay, so what causes processes to go between levels of the queues? So, like I said, when a process arrives in the system, it'll go into priority 0, the top priority queue. And when it executes, if it executes to completion of its time slice, so it uses the CPU for the whole time slice, it will be preempted by the CPU, so it'll be interrupted and then placed in priority 1 queue. So it'll be moved down 1 priority level. And that will keep happening. Every time a process executes and uses its entire time slice, it'll move down a priority level until it reaches the lowest priority. And obviously it'll have to stay there. What could cause a process to move up the queue? Well, at this point we probably need to introduce other things. So in a typical scheduler, one reason for a process moving back up a priority level would be if it didn't use its entire time slice because it was interrupted, because it performed a blocking I/O operation. So we have a process executing at priority 1, it's happily using the CPU, and then it performs an I/O operation that blocks at that point and gives up, voluntarily relinquishes the CPU. The scheduler will then move it back up a priority level so that the next time we're looking for a process to schedule, assuming that process is ready, it'll get a higher priority. And so this will tend to preferentially execute processes that are dependent on I/O. And that's usually a good thing to do. If a process is using I/O and the I/O operation is completed, it's usually a good idea to schedule that process again soon. Okay, so this will tend to prefer short tasks. So very short tasks will go into priority 0, they'll execute, they'll finish, and that will be the end. And they'll tend to jump ahead of the queue compared to longer tasks that are going to be moving up and down the priority orders. And again, we have this property that very long-running tasks may be starved if we have a lot of short-running tasks constantly arriving in the system. But that's the goal of having these increasing levels of time slice is to, once a process finally gets access, once we've been through all the priority 0 tasks, we're going to give a good long time slice to our long-running process to give it a chance to get some work done. Okay, so if we apply this kind of approach, we see very good initial response. So again, if we're thinking of an interactive system, we'll get a very short time to the initial execution for any process. But long-running tasks that need a lot of CPU time could be starved, and they will tend to have quite long turnaround times overall. But the average turnaround time in this case is going to be very good because most of our tasks are actually short-running and they're going to be preferentially executed very quickly. So we get a good average, not so good upper bound on our turnaround time. Okay, so this is really the basis of a lot of operating system schedulers. The Linux operating system scheduler is a little bit more complicated again. And I should probably just show the difference here. This first scenario, sequential, is where a process isn't actually allowed to ask for access to the CPU until the previous one of that process is executed, whereas overlapping, we see here the green task is asking for access to the CPU before the previous green task is actually executed. Either way, you get potentially very long maximum turnaround times, but reasonably good average turnaround times and very good initial wait times. Okay, so that was a lot of different methods, a lot of different algorithms, and we can compare them in different ways. Like I mentioned, depending on which criterion we're most interested in, we might choose a different algorithm. And so you can order them by potentially the maximum of the waiting time, which is these blue bars, or the average of the waiting time, which is the black bar in the middle. We could order them by the maximum of the turnaround times, the red bars. We could order them by the average of the turnaround time, which is, again, the black bar in the middle of the red bars. So this is just, I don't know, roughly, let's see, the ordering here is the maximum wait time. So the maximum blue bar, you can see there, the right-hand sides of the blue bars are stepping out gradually. And so if maximum wait time is what you're interested in, and this might be the case, say, in an interactive system like a phone where you're dealing with a user, you can see that actually the feedback, the multi-level feedback queue, these are giving you the best maximum waiting time. So they're the most responsive scheduling algorithms. Our nice, simple first come, first serve algorithms are right down the bottom. So they're giving us terrible maximum waiting times. So just because of the, we're not preempting, and the order in which our processes come in is going to make have a big effect on the wait times. And so first come, first serve performs really badly here. Round robin, as we saw, performs pretty well, and the rest of the methods are kind of in the middle. Okay, but if we are interested in average case response times rather than maximum response times, we actually see that shortest remaining time performs best of all. The multi-level feedback queue is still doing pretty well. Round robin is still doing pretty well, and again, first come, first served is still worst. If we're interested in turnaround time, so it's really important to us that we don't have a very long wait time to complete any job for whatever reason. First come, first serve now looks very good. It comes absolute top with the shortest red bars here. Whereas our feedback queues are now looking pretty terrible. For some of our jobs in multi-level feedback queues, we get exceedingly long maximum turnaround times. As I mentioned, we can have jobs being starved because shorter jobs coming in are constantly getting access to the CPU. So we've almost inverted the order there. And then again, if we look at an average turnaround time, okay, the feedback queue's potentially not looking quite as bad. Now first come, first served is looking terrible again, but shortest response time, shortest remaining time is looking best. So the average turnaround time is best if we can predict the computation time of every process and we can use shortest remaining time first, then we get the best average turnaround, which means the best throughput. So yeah, if we're interested in a transaction system, something that's just processing a very large number of transactions and we're just aiming to get throughput, for example, I don't know, banking clearance system or something like that, we might be interested in these scheduling algorithms that provide short average turnaround times. Okay, so it really depends on your system and what your criteria are as to which algorithm you might choose. And this is one of the reasons why, as Nick mentioned, scheduling is a research problem. We're still finding new applications, and therefore we're still finding new scheduling algorithms for which that work best for those applications. Theodore, yeah, I imagine there will be similar kinds of constraints for any resource. So you're thinking about a resource like a channel like Bluetooth, where you've got a limited amount of bandwidth available, you've got limited access to your network controller or your hardware device. Yeah, you'll have to perform some kind of scheduling of that device as well. And whether that's done for you by the operating system using its regular scheduling, or whether there's an additional or different scheduling algorithm applied, I'm not entirely sure, but yeah, some scheduling will be required, obviously, to multiplex or time slice your applications that are trying to get access to that device. Okay, so just to summarize, here is everything in a kind of a nice, simple table. I won't read through all of this, but just sort of drawing your attention to the fact that we have properties that are, we have properties in terms of what we need to know about the processes themselves. So whether we need to actually know the computation time, these three methods at the bottom, you have to know the computation time to be able to schedule. The three methods at the top, you do not, and therefore the three at the top might be more useful for general operating system scheduling. You also have a question of whether your scheduler allows preemption, whether you can interrupt a process before it's completed. If you can't, some of these scheduling algorithms are not possible. And then you've got your various criteria for whether you're interested in wait time or turnaround time, whether you're worried about starvation. For each of these properties, different methods will tend to be a better choice. Okay, so this is just a nice kind of overview on one slide. Okay, I'll just stop briefly before we go on with a discussion of predictable scheduling. I'll just quickly check through the questions if anyone has any questions about any of the algorithms that we looked at. Okay, so Xiangyi's asking about feedback queue. So, right, if we have new processes arriving in, say, priority 0 or priority 1, that they're going to take precedence over any processes in priority 2. So that's why we have that risk of starvation. We're not going to look at priority 2 until we've dealt with those processes in priority 1. So this is certainly a risk that we can wait an exceedingly long time for lower priority processes in that case. Okay. So we talked about criteria around trying to bound maximum times or trying to reduce average times. So if we carry on the thought of trying to bound maximums on things, so we're trying to place absolute constraints on certain criteria, we might be interested in a situation where we really want a form of predictable scheduling so that we can make certain quality of service guarantees. And these might be things like how quickly our system can produce data, or either ingest or produce data as results. We might be interested in reaction time. So we have an interactive system where a human is using it. The reaction, or we have a system that's connected to the physical world. The time for the system to react to an external event could make a big difference to quality of service. As I'm sure you've all experienced when you're using your phone or something. On those rare occasions where your phone is unresponsive for longer than you expected, it makes a big difference to your user experience. If you click a button and nothing happens, and if that frequently occurs in your phone, I mean, the first time it happens, that's a surprise. But if that's happening all the time, you might start to grumble and say, this is a crappy phone and I'm going to have to get a new one. Start getting angry at Apple or whoever made your phone. And it really makes you feel unhappy about that system if it's unresponsive and the reaction time is longer. Moving to kind of another extreme where we've got an embedded system controlling a physical device that's interacting with the world. Again, the example of the car computer dealing with you slamming on the brakes as a user. the difference in reaction time could literally be life-threatening if you take a long time to react to that event. We might also be interested in deadlines, and so a deadline, is more about the turnaround time. So a given task or process must have completed execution by a given time or within a certain amount of time after it was requested. And we might have delivery times for different results. So we may have a process delivering multiple results at certain guaranteed times. And so we might want to either guarantee the actual times or the bounds of the times in which things happen, or we might want to provide bounds on variation. So we might want to say it's okay to deliver results within a certain time frame, maximum and minimum, or something like that. Okay, and so apart from those examples I already mentioned, some very common examples for these kinds of quality of service are things like media. So right now, I'm streaming to you through OBS. OBS is delivering video stream to the restreaming internet service, which in turn is passing that on to multiple different endpoints at YouTube and Twitch and Microsoft Streams. So there's a lot of things going on in between, and there's a lot of, unfortunately, there's a lot of hops between my camera and you. If any one of these services exceeds certain bounds on its responsiveness, so it takes longer to process a particular packet of data than whatever an acceptable time is in terms of microseconds or milliseconds, you're going to experience that as a lag. So some of you are experiencing that right now. You'll experience jitter or breaks or pauses in the delivery where it appears that I'm not doing anything. That's pretty annoying, but you can deal with it in a lecture, particularly if it's recorded. It's much more important to advertisers and to people doing live broadcasts. If they get a lot of laggy behavior, they're going to get viewers turning off, not watching the ads, not paying attention to the ads, and therefore the advertisers won't pay money. And again, we could have situations where you can imagine it could be life-threatening to have those kinds of breaks in scenario. And again, we've got situations where we're dealing with responses to alarms, and we might have guaranteed times that we need to respond to an alarm. So for all of these reasons, we're going to have we have a requirement for some kind of predictability in scheduling, and so we start to get into real-time scheduling. This isn't the real-time course, but it's worth thinking about what some of these constraints might be. And so we can start to name some of the attributes that we might be interested in. So Harry's thrown in a great example there. Telehealth, perhaps not immediately life-threatening, but not great. Right, so I guess you could expand on that a little, Harry, the kinds of telehealth you're thinking about. I'm thinking of a couple of different kinds that you might be talking about. So the first one might be you've got an interview with your doctor, a specialist, and you're conducting it over a camera, Zoom or something like that. You may have, say, a doctor sitting in the room with you, talking to a specialist in another city, and the specialist is assisting with the delivery of medical care. In that case, as you say, maybe a delay is not life-threatening. It just appears like a lag in the video or something like that. And if too many of those happen, it's going to make it difficult to conduct the conversation, and the overall quality of service might reduce because it's just hard for your doctor in the room and the specialist to talk to each other sensibly. Right, so you might get the wrong, you might not get a great quality of care if that kind of thing happens. I can think of another kind, which is where you've actually got, say, a robot performing the physical operation being controlled by a doctor in another location. So a human operator over a network. In that case, I could imagine actually that the delays or failures to respond could actually be life-threatening in some scenarios. I can imagine, if a robot performing surgery drops out halfway through the operation, I don't know, you've cut a vein and you haven't yet stitched it up or something horrible like that. I could imagine that being life-threatening. So I think any case where you're controlling objects in the physical world, and those objects are used in a safety critical system, yeah, I think that could be those kinds of real-time constraints on responsiveness could really be life-threatening. Yeah, sorry, that's a pretty dark scenario, but I'm sure the people who build these telehealth systems are having nightmares about this all the time. So yeah, real-time constraints are important. So what kind of attributes are we interested in? We might be thinking about delays from when the task is created. So when it, when the system first becomes aware of the task to when it's actually begins executing on the system. And so we might be interested in either in minimum or maximum. I don't know, perhaps minimum if we're requiring that the task doesn't start before a certain time, but maximum is probably more important, that we need the system to be responsive in real time. We might also be interested in elapsed times. So from when we started executing to when we complete execution of the task, or from when we get access to the system to when we next get access again. If we've got say a task that requires regular access to a resource in order to make progress and complete its requirements, we'll be interested in those elapsed times between when it's executing. And finally, the maximum execution time, so how long it actually takes for the process to complete whatever it's doing. And then of course, the deadline itself, which is what is the absolute last time at which a result from this process is useful. So if this process has not completed what it's doing before the deadline, then it may be that it's absolutely useless to us. A result too late is just as good as no result at all. And again, you can imagine the scenario of the car and the brake. If your result of pressing the brake is delivered to the actual brake pads after your car has hit a wall, it's clearly no good, and your real-time system has just completely failed. Okay, so actually I'll kind of skip all this scenario, and we'll just go on to talk about temporal scopes. So we could think about processes in terms of periodic temporal scopes. So this is the case where we're interested in events or processes that happen on a regular basis. So something like a controller for a physical system is very likely to have some kind of periodic behavior. Check every n units of time for the value of a particular sensor, and then perform some operation based on that result. And so a lot of physical systems are strictly periodic. They operate in a clock like this, and they take certain behaviors, they execute certain processes exactly on a period, on some multiple of the clock cycle. There are other kinds of systems that are on average periodic but not rigidly timed. So these might be, these are kind of softer systems. They might be occurring in response to processes outside of the system that are regular, but there's no sort of direct lockstep synchronization between our computer system and the regular process that's happening in the real world. Yeah, I think in general terms, if you're synchronizing together two different systems that have different clocks, you're going to tend to have drift between those two systems, and you're never going to have a perfect lockstep synchronization. So in this case, we may need to treat the behavior as aperiodic. And then there's other kinds of systems which you could just treat as sporadic or transient. So these are things that we just have no idea exactly when the next event is going to happen. It could be immediately, or it could be in some years' time. But when an event does occur, we need to respond to it within a certain real-time frame. So these would be things like user requests. You press a button on your phone. Or an alarm, something, a temperature alarm kicks off in your environment control system in your building, or some kind of interaction through I/O with the real world. So none of these things are predictable. They're all being initiated by events outside of your system, but you may have real-time constraints in responding. Okay, and then in terms of those constraints, so we were talking about the deadline. The deadline could be hard or firm or soft, and these are all terms that people use in real-time systems, but they tend to be defined slightly differently depending on the exact system you're talking about or the exact safety standard you're talking about. But typically you might use the word hard, a hard deadline, to indicate that even a single failure to perform a task before the deadline could be considered a severe malfunction or a catastrophe, a disaster. So the card brake system is a perfect example. If your card fails to respond to braking within a strict deadline, that's very likely to lead to a crash and potentially loss of life. So that would be considered a hard real-time system. It would be an absolute disaster, a complete malfunction for your car to miss one deadline on braking. So that's at the sort of the very extreme end of real-time systems, and this is what most people would think about when they're talking about real-time system scheduling. There's another term, firm, that's sometimes thrown around, which indicates that in general the result of your process is meaningless or useless if you've passed the deadline, but it might not be considered as a catastrophe or a permanent failure of the system. And so, I don't know, maybe an example here might be something like a weather forecast system or something like that. It's no good to you if I deliver you the weather forecast for today. If I deliver it to you tomorrow, that's clearly meaningless. So there may be deadlines after which the result is just no good. And in fact, a weather forecaster might not get paid if for a service they're providing if they fail to provide that service by a given deadline. So there may be a commercial quality of service involved here. However, when we say they're meaningless, it may not lead to loss of life if the weather report is delivered 5 minutes late. It may just be that it means that it can't be used as inputs to further processes that are going to require it. So it might not be considered a catastrophe. I don't know, perhaps from the weather forecaster point of view, who's not getting paid, maybe that is a catastrophe, but perhaps the customers can still survive. And then there's a third form of soft real-time systems in which you may have a deadline, but the results may still be considered useful. And this is not really a real-time system. This might actually be another way of saying that it's not really a real-time system at all, and the deadline isn't actually that important. And this, so this is actually getting back into what I would think of as regular scheduling. These might be things like soft deadlines that, say, Google might put on your search, on returning a search result for a particular search query. So Google knows that commercially you'll get very angry if your search takes 5 seconds to complete, and you'll think that Google's a crappy service, and it'll reduce your experience as a customer. But really, nobody's going to die, and in fact, the search result is still perfectly useful to you. So in that case, you might think of that as like a soft real-time constraint, but it's really not a real-time question. Okay, Nicholas has thrown in a useful comment about scheduling of network resources and multiplexing data across there. So showing you these criteria are really for the criteria about deadlines are really applying to individual processes. And so you could imagine, I guess, a real-time system that's made up of many processes, each with different kinds of deadlines. And some of those deadlines could be hard and some could be firm. So yeah, your car system might be a perfect example. There'll be certain real-time constraints that are hard, like the brakes, and there'll be others that are only firm, like I don't know, there may be other systems that you're willing to accept occasional failures in responding within a certain deadline. Perhaps an example might be controlling the windows or something like that. If you press your window button and it fails to respond within a second, again, that's leading to a very poor user experience, but it's not going to kill you. Whereas there are other systems that will have hard constraints. And so those different real-time constraints could lead you to apply different priorities in scheduling, or even different scheduling algorithms. You may choose to separate the real-time parts of the system from the soft or firm real-time parts of the system. And this is actually another reason why you'll find a lot of embedded systems, we mentioned this right at the beginning, a lot of embedded systems like cars tend to use large numbers of small, predictable CPUs. They're very simple CPUs that have predictable computational behavior. They don't do complex things like reordering or multiple levels of caching. And the reason why is that those systems are much easier to predict the timing constraints, and therefore you can actually place hard real-time deadlines on them. It would be a really bad idea to have your car braking system operating on the same computer as your stereo, for example, so that the responsiveness of your brakes depended on what track you're currently playing on Spotify. That would clearly be a terrible idea. This is why the car designers tend to separate the systems. Okay, that's really all I wanted to say about scheduling, unless anyone has any further kind of questions. Look, Matthew, I didn't actually get to multi-CPU scheduling. If you are interested in multi-CPU scheduling, so there's this great book, Operating Systems. You don't have to buy this in a book, by the way. I was kind of silly. This book, Operating Systems, 3 Easy Pieces, is available online. You can go to the website, and I'll actually show you where that is. Because I have linked to it a couple of times already from the lectures. So, for example, this module that we're doing right now, scheduling. If you look at the references, you'll find that I've linked to this chapter, multi-level scheduling. And I'm going to just copy the address here because I want to show you the site. This is a wonderful open source, completely free book rather that's available to you about operating systems. And there's a lot of stuff in here that will be quite useful to you in this course. So we've got a whole section, multiple chapters on concurrency. We've got whole sections on scheduling in operating systems, including one chapter on multi-CPU scheduling. So Matthew, if you're interested to find out more, that's probably the place to go. And of course, hopefully you'll be able to do the operating systems course here at ANU in later years. Okay. I think I'm trying to decide if I should leave it there or if I should quickly show you about Chapel Atomics. So completely switch. Yeah, who's interested in Chapel Atomics and Chapel synchronization variables, which we're using for this week's lab? All right, let's take a really quick look at Chapel Atomics. I think that could be useful for those of you who maybe having trouble or haven't yet started on the Chapel lab for this week. Okay, so we're switching gears entirely. This is not about scheduling anymore. This is about some low-level mechanisms that are provided in the Chapel language to allow you to synchronize between different tasks running in a Chapel program. and also to ensure atomic access to data. So these are clearly two very important things that we want to do in a Chapel program where we have multiple tasks. And one of the things that I haven't actually shown you yet in a Chapel program is how to create multiple tasks. I've shown you how to do it in a data parallel sense. So we can create data parallel loops using the for all statement or just using a reduction, and sometimes promoted operators. But if you just want to create tasks to actually do a piece of code, in Chapel it's dead simple. We can use a statement cobegin, and that will generate a set of tasks for each statement. So why have I put these brackets here, these braces rather? It's to make it clear that this is one statement, and this is another statement. Everything in between these braces is going to be executed as a Chapel task, and everything in between these statements is going to be executed as a separate task. So Chapel will spawn two tasks to execute these two statements. So multitasking in Chapel is really that simple, to explicitly spawn tasks. Okay, so imagine we have two tasks. I'm going to go right back to that counter example that we had at the beginning. So imagine we have two tasks that are both operating on counter, and they're both incrementing that counter. So, and in fact, okay, we'll have a for loop for I in 1 to 1,000. We're going to increment the counter. And we'll do this in both of them, actually. Yeah. Okay, so now we have two tasks, both operating on a shared variable. So this is the scenario that we had right back at the beginning when we were looking at creating threads in POSIX in C. And we found that this is in general a bad idea because this increment statement is actually a complex operation where we read the counter, we add 1 to the value that we read, and then we write it back again. And so you can imagine that in a Chapel program, if we were to do this and then write out the result with the counter at the end, okay, maybe this will work. Maybe, hang on, I need to install Chapel by running the set chapelin bash script so that I know where to find my Chapel compiler. Okay, so maybe this will work nicely. Maybe we'll get the expected result of 2,000 for our counter. Or maybe we'll get a race condition and we'll actually end up with some weird result. Now, one of the nice things that Chapel will do is actually point out that my code is incorrect. So the Chapel compiler, remember, Chapel actually has concurrency as part of the language, so unlike C. And so the Chapel compiler looks at my code and complains. It says the shadow variable counter is constant due to task intents. So what that means is, because we declared counter out here as a variable that's shared, that's available and in the scope of both of these tasks, but on creating a new task, we're actually not allowed to copy in, at least by default, we can't copy in our counter variable as a modifiable variable within each of those tasks. So Chapel knows that this is shared and that incrementing it in this way would lead to a race condition. So it's complained. Okay, so Harry's already found a way that we could solve this problem, which is using sync variables. I'll come to sync variables second. So I called this program atomic because I wanted to show you how we can use this, how we can use atomic variables in Chapel to do this. So to use an atomic variable is really simple. We just stick the keyword atomic in front of it. Unfortunately, we can't now do direct assignments to an atomic variable. So if I try to compile this, I'll get a different kind of compile error because you can't simply assign an atomic variable in Chapel. It's not going to, that sort of is meaningless now for an atomic variable. But what we can do is call any one of a number of nice atomic operations that Chapel provides. And so if you want to find out the full list of atomic operations, you can follow the link from this week's lab to the list of atomic operations. We've listed some of them here, but there are actually even more listed up at the Chapel website. And you can find out all about atomic variables here. And so the particular thing that we're trying to do in this case is we're actually trying to just increment the variable, which means fetching the current value and adding 1 to it. And so we could actually just call the add operation on this atomic variable. So we'll do that in both cases, and actually my code is really horrible here. I'm going to turn this into a Chapel procedure just to make things a bit nicer. So this is going to do the increment that I've got there, and so I can call this twice. And I keep forgetting my syntax. It should be a brace. Okay. So okay, we've got a procedure now that does that incrementing, and I'll call it twice. Once for statement 1, and once for statement 2. So actually simplify our code a lot. Okay, so it's important to realize that these two tasks, each of these statements is executed in parallel. So this call to the procedure Miller and this call to the procedure Miller is going to be done, each of those are going to be done as a separate task. Okay, and in those tasks, we're going to be adding 1 to that atomic counter variable 1,000 times. Okay, so right, now we compile a code. We're using a correct operation on our atomic variable, one of the ones that's defined here at the Chapel spec. And importantly, that adding 1 to the value is going to be done entirely atomically. And so hopefully when we run our code, at the end, I can guarantee you, in fact, that we'll always get the value 2000 for the counter, because now all of those updates that we're doing are being done atomically with respect to the other task. So that's really nice. That's about the shortest program I've ever seen to do this kind of increment. And if you remember back to the POSIX threads example, how much longer that was, and it didn't even achieve correct atomic behavior. Okay. So Brian was asking how is this proc different? This is just saving me. So I could replace each of these calls to the procedure. I could replace them with the code that's there. Obviously, I mean, a procedure is just a chunk of code that you can call. So the important thing to realize is that each call, each statement in this cobegin is being executed as a separate task. So you can think of this as sort of imagine there's a piece of pseudocode here that says begin task for each of these. So it doesn't matter how many tasks I put in the, how many statements I put in between these cobegin braces, each one of those statements is going to be executed as a separate task. Okay, so it's basically switching our default behavior from sequential execution, one statement after the other, to parallel execution where we're doing them all at the same time. Okay. Okay, so if I don't declare this as atomic, so we get rid of that atomic, that's going to give us that same compile error that we had before. Okay, so sorry, Wenshi, I missed the other part of your question. So if you don't declare it as atomic and you get rid of the cobegin, well then you just have a sequential program that is incrementing the counter by 1 1,000 times, and then it's doing it again. So you'll get the same result, you'll get 2000, but you'll only have a single sequential task to do all that work. Right, so that would be okay. If you got rid of both the atomic and you got rid of the cobegin, then your program would still be correct. But if you just get rid of the atomic, we would get the same compile error that we got before. Okay, cool. So that's the way to do things with atomics. That's really nice and simple. I just wanted to show you the other suggestion that we had from Harry, which is how to do things with sync variables. So sync variables in Chapel are, sync stands for synchronization. So as you can imagine, these variables can be used to synchronize between different tasks in a Chapel program. So again, we're going to create 2 different tasks in Chapel, and this time I will actually put them in between braces like I had before. So there's task 1 and here's task 2. Okay, so what are these tasks going to do? Okay, I could do the counter example. I'm actually going to do something slightly different because I want to be able to show you the exact ordering of things. So remember, with synchronization, we're going to enforce an ordering, and I want to be able to show you the exact order in which things are going to happen. So I'm going to create a variable, which I'm going to call a postbox, and this postbox is going to contain a single value, which is an integer, but it's going to be a sync variable. So it's going to have the word sync in front of the type of variable, and that tells Chapel that it's got some additional properties. So a sync variable has, in addition to the integer value, it's now also got the property of being either full or empty in Chapel. So a sync variable is going to start as empty. If we don't initialize it, it will start as empty, but when we write to it, it becomes full. And when we read from it, we can set it back to empty again. So we can sort of alternate between these 2 states, and we can use that empty full status to synchronize between tasks in our program. And actually, it's traditional, it's like convenient for Chapel programs. When you have a sync variable, just to stick a $sign on the end of the name, just to let people know that this is a sync variable, and therefore it's probably got some meaning in terms of synchronizing bits of your program. Okay, so we've got a postbox. And now we can have 2 different tasks. One which is a writer. In fact, let's just have the writer print out that it's what it's doing. The writer is going to write a value into the postbox. So the writer can call this function that Harry mentioned. It's called write empty full. And so what that does is it both writes a value, and it doesn't really matter for our purposes what the value is, so we'll just write 17, but it also sets that synchronization variable to full. So now it has a value. Okay, and then at the end we'll obviously just print out that we're finished. Okay, meanwhile the reader is going to, as you might expect, read the value of that variable. So we'll have a reader task. It'll print out when it starts. It'll read the value from the postbox. And to do that, we can just create a new variable and call that other method that Harry mentioned, read full empty. So this is going to do 2 things. It's going to read the value that is currently stored in the postbox, and it's going to set the postbox back to empty again once it's successfully read. Okay, and then again at the end we'll just print out that we're finished. Okay, so far so good. What's going to happen if the reader reaches this line where it's trying to read from the postbox before the writing task has actually reached this line where it writes a value to the postbox? In that case, because the postbox starts uninitialized, because it starts empty, the reader is just going to block on this line until such time as the writer writes. So this is how we synchronize tasks in Chapel. Okay, so I should be able to compile this example at this point, and I probably should have actually printed out the value of the message that I read. Yeah, actually, let me fix that up now. I'll just print out that I read this value. Okay, I'll compile my code so that we can see the value that got read. When she says, looks like a pipe. Yeah, it's very similar to the channel idea, I guess. This is a very limited form of a channel. It's a channel that has a single value, and so it's connecting together two tasks. But I guess, yeah, maybe pipe is more correct in that any task could be reading and any task could be writing. So it doesn't. We're not enforcing which particular task is at either end of this post box. And I've clearly missed something. Oh, because I didn't put the $sign on the end of my variable name in either case. So I got the name of that variable wrong. Okay, so it's important to realize we're creating two tasks. They're going to run in an arbitrary order. We don't know. But one thing that we can say is that anything that happens before the read in the reader task is going to happen strictly before anything that happens after the write in the writer task. So we have that synchronization. Okay, so we see both the tasks printing out. The reader reads the value that was read, and that's all good. How can we prove, or how can we check the ordering? I'm going to just add one more element to this program, which is we're going to put in a bit of a delay so that we can actually see the ordering in which things are happening. And for this, I'm going to use a package in Chapel called time, which could be useful. This allows us to do a bunch of things, including measuring particular times, but it also allows us to do our familiar sleep operation. So we can ask a task to go to sleep for a particular period of time. And so we're going to ask this task to go to sleep for 2 seconds before it reads a value from the post box. And the other thing I'm actually going to do is have the writer write 2 messages. So I'm going to write the first message. I'm going to print out that we wrote the message, and then we're going to write another message. And again, it doesn't really matter what the value is because we're just using this for synchronization. But again, after the reader reads the message, it's going to read another message and then print out the value of that as well. Okay. Why do we need those 2 messages? It's really so that we can demonstrate the fact that our reader is going to cause the writer to block on that first message. So, oh sorry, the other way around, on the second message. So, whatever order we come to here, the reader is going to take 2 seconds before it calls the read method. And what that means is that even if the writer successfully writes immediately to begin with, we expect that there'll be a 2-second delay until it can write again, because this write empty full method procedure can't complete until the post box is empty and can be set to full again. So we'll call write EF once, that's going to set it to full, and then we'll have to wait for the reader to call this read method before we're able to write again. So we should see that 2-second delay now in our postbox program. Okay, so we see that when we run the program, I'll just do that one more time, a little more slowly. So when we run the program, we see that the writer starts, the reader starts, the writer writes a single message, and then there's a 2-second delay. And after that 2-second delay, the writer is able to end, and because it's managed to write the second message. And so that 2-second delay is happening again because the reader waits 2 seconds before reading that first value. So for those 2 seconds, the writer is blocked here at its write a second call on write EF. It's waiting for that postbox to become empty so that it can write another value into it. Okay. Oh, I'm losing the terminal. Sorry about that. Okay, let me just double check in OBS so that I can make sure that you can see it. Okay, let me run that one more time. So we see the writer starting, the reader starting, and then a 2-second delay before everything else happens. Okay, hopefully you caught it that time. Thanks. Cool. All right, so you've got those two different options there. Atomics, if you want to ensure atomic operations on particular variables, not just integers, but floats as well, and booleans, of course. And you've got synchronization variables or sync variables if you want to ensure some ordering of operations between different Chapel tasks. There's another kind of sync variable, I won't go into it now, but it's called singles. You'll also find, if you go and look at the task parallelism sections of Chapel, you'll find out about single and sync variables. Any questions about any of those before we go? I'm hoping that'll be coming useful for you in this week's lab. Okay, now that you know about how to create Chapel tasks to do anything you like and how to synchronize them, you've got data parallelism. You can actually write quite a complex multi-core Chapel program. Yeah, Shang, you can ask about things from the last lecture. In fact, I think, did you ask right at the beginning? There was a question I ignored right at the beginning of this lecture. Okay, so this is the question about promotion. Okay, I think this is, yeah, so this is sort of relating to, okay, so the question is, with Chapel operator promotion, is this only defined if we explicitly define the element type of the input iterator? So I think that's relating to, we were looking at that, one example of this question might be, we were looking at, in the game of life, I think, we were looking at the question of why the count procedure call wasn't being promoted if we passed. So as we had originally defined it, we defined the count procedure as a generic function, so we didn't actually define the type of C. And so we found that it would only be promoted if we passed in an iterable domain, an iterable object. It would only be promoted over that iterable object if we defined the type, in that case to be cell. I think that's probably true. I think for the compiler to be able to promote an operation, it would need to know the base type of that function. So it would need to know the type of each of the parameters before it was then able to promote this to operate in a data parallel fashion over an iterable object. Yeah, I think that's correct, Shem. Just trying to think of why it wouldn't work. A good way of explaining why it wouldn't work if you didn't know the type. I think my best way of trying to explain why we couldn't promote, if we pass in an iterable value as C, and then a cell as the parameter match, the reason why it wouldn't promote is because it would first assume that we're instantiating a generic function here, with C being, in this case, I think it was an array of cells defined over a particular domain, and it would then try to compile this as looking for an operator equals defined over this iterable object, the array, and on the left-hand side, and a single cell on the right-hand side. And the compiler would find that no such operator is defined. it would then try and promote this. So the promotion in that case is going to happen as, okay, now we know the types of each of these things. C is an array, it's an iterable thing. The right-hand side is a single value, so it would try and promote this operator. And that's where things went wrong. So when we promote this operator, the result of the promotion is actually itself an array. And so that's why we got that compile error, where we defined our procedure as returning a single binary range, but actually the result of promoting the equals operator, the result of promoting this entire expression would be an array of binary ranges, and that's what led to our compile error. Okay, so yeah, very short way of saying, yes, the compiler must need to know the actual type of the expression before it's able to promote that over an iterable object. Okay. Yeah, for more details, see the compilers course. All right, I'm going to leave it there because we're quite a long way over time. But thank you for all your questions, and good luck with the Chapel Lab this week, and I'll see you next week. Thanks, everyone.